In this video and in upcoming few videos, we will discuss completely about quicksort. So quicksort is a sorting technique where we get a collection of elements and we sort them in ascending or descending order. So in quicksort, here if you see, when we discussed merge sort, we saw that it was a divide and conquer algorithm. So by divide and conquer we mean that let's say if we are given a complex problem, we try to divide that complex problem into smaller sub-problems, and when those smaller sub-problems are not further divided, we try to conquer them. And when we conquer each and every smaller sub-problems, we reach to the solution of our original problem. So quicksort is also a divide and conquer algorithm. It involves 3 steps. The first step is the pivot selection. So in pivot selection, what we do is we pick an element from the array and mark it as pivot. Now this pivot element can be the first element, last element, or any random element. We just take any element and mark it as pivot. So here, let's suppose we are given this array and we want to sort this array using quicksort. So as we discussed, the first thing we do is we take a pivot element. Now this pivot element can be the first element, any random element, or the last element. So we can take any element as pivot. In this tutorial we will take the last element as our pivot. So here the last element, which is at index 8, the value is 3. So this is our pivot. So this is the first step. We take a pivot and we can take any element as our pivot. Now after taking a pivot, what we do is whatever the element we have taken as pivot, now we actually partition the array. So by partitioning we mean that we reorder the array such that all elements greater than pivot comes after the pivot, and all the elements smaller than pivot comes before the pivot. The elements equal to pivot can go either side of the pivot. So whatever the pivot we took, which we saw in our previous slide, it was 3. So then we partition the array in such a way that all the elements which are greater than pivot comes after the pivot, and all the elements which are smaller than pivot comes before the pivot. So we are actually reordering the array. And the elements which are equal to pivot can go on either side. It can go on the left side or on the right side. So why we are doing this partitioning is, this is the important step. After we perform the partitioning, the pivot is actually at its correct sorted position. Now what it means is, let's say 3 is the pivot and these are the remaining elements. So all the elements greater than pivot should come after the pivot, and all the elements which are smaller than pivot should come before the pivot. So here 3 is the pivot. So now we'll check 9 is greater than pivot, it comes here. Because as it is greater than 3, we know that all the elements which are greater than pivot will go after the pivot. -3 is smaller than 3, it comes here. 5 is greater than 3, it comes here. 2 is lesser than 3, it comes here. 6 is greater than 3, it comes here. 8 comes here. -6 comes here. 1 comes here. And 3 is the pivot, so it is at this position. So here you can see these are all the elements which are smaller than pivot, and these are all the elements which are greater than pivot. We are not concerned about the order of the elements. Here it's -3, then it is 2, then it is -6. So we are not concerned about the order. Here it is 9, 5, 6, 8, like this. We are only concerned about the partitioning of this array in such a way that this is the left part which is smaller than pivot, and this is the right part which is greater than pivot. So why we are actually doing this partition? Here you can see, I'll just remove this. So when we actually partition the array based on what we discussed, here you can see that 3 was our pivot. All the smaller elements are just before the pivot and all the greater elements are just after the pivot, and it can be in any order. But here you can see that after this partitioning, one unique property with this pivot is, let's say this is low index and this is high index and this is any jth element. So after this partition, in this array from low to j minus 1, which is this portion, is less than equal to array of j, which is our pivot, which is less than equal to j plus 1 to high, like this. So when we do this partition, this holds true. And if you see, when we sort this array, so this is the sorted array. So the elements are arranged in ascending order. But here you see that the difference between this partitioning and this sorted array is the pivot after the partitioning and after the sorting doesn't change its position. It's actually at its correct position after the first partition. So here if you see, 3 was our pivot. After partitioning it came at index 4. And if we sort this array, you will see that in the sorted array, the pivot doesn't change its index. It will still be at index 4. So this is one critical information about quicksort, that it partitions the array and all the elements which are smaller than pivot comes to the left and all the elements which are greater than pivot comes to the right. But this pivot after partition is actually at its correct position even after the array is sorted. So this is the second step of quicksort, the partitioning step. Moving ahead. Now here you saw that this pivot and this partitioning, it is actually the divide part of the algorithm where we are actually reordering the array in the partitioning step. And now how we will conquer this is based on this recursion step. Whatever we did above, now we recursively apply the above steps on the subarray formed on the left side of the pivot and on the right side of the pivot. So these two steps we will apply on all the elements which are lesser than pivot and on all the elements which are greater than pivot recursively. So this step which we discussed, that after this partitioning the pivot is at its correct sorted position. We don't touch the pivot after the partitioning. We take the left part of the pivot, we take the right part of the pivot, and we apply the above steps recursively on the left side and on the right side. So here pivot in the sorted array is at its correct position like this. But when we do the first partition, this one particular element is sorted. Here you can see in the sorted array, pivot doesn't change its position and it is at its correct position. So we can think from the first partition, we have sorted one element. And now when we are discussing the recursion part, the third step, what we do is, we take the left side of the partition, we take the right side of the partition, we leave the partition as it is at its correct position. Now we apply the same steps of choosing a pivot and then partitioning on the left side of the array and on the right side of the array. So this we keep doing recursively till all the elements are at its correct position. First partition gives one sorted element. If we do this recursively with the left part and with the right part, there will be a time that all the elements will be properly sorted and they will be at its correct position. So the recursion step is important. So these are the three important steps in quicksort: pivot selection, partitioning, and then doing the recursion of these two steps on the left side of the pivot and on the right side of the pivot. And when this recursion will end, all the elements will be properly sorted and they will be at its correct position. So this was the basic introduction of the quicksort at a high level. In our next video we will see how we do this pivot selection and the partitioning. And after that we will see that how this recursion help us in sorting the array, taking the help of these first two steps and applying them recursively. We are going to discuss that what is quicksort partitioning. In the part 1 of this video, we discussed a basic introduction about quicksort. So in this video, we will be discussing what is quicksort partitioning. So friends, in our previous video, we discussed that quicksort is a divide and conquer algorithm, which basically involves 3 steps: pivot selection, partitioning, and recursion. In pivot selection, we actually pick an element and mark it as pivot. The pivot element can be the first element, last element, or any random element from the array. And the second step is the partitioning step, where we reorder the array such that all the elements greater than pivot comes after the pivot and all the elements smaller than pivot comes before the pivot, and the elements which are equal can go on either side of the pivot. So usually in the partitioning step, we actually get a left part and a right part, and in the middle we have pivot. So once the partitioning is done, pivot is somewhere in the middle. Also we discussed that after this partitioning, the pivot is at its correct sorted position. So here you can see at whatever index pivot comes after the partition, if we sort this complete array, the pivot will lie at the same index only. So it means after the partitioning, one of the element is sorted. So in the recursion step, we apply this pivot selection and partitioning recursively in the left side and in the right side, and we keep on doing that till the complete array is sorted. So in this video we will see that how we do pivot selection and partitioning. So let's say we are given with this array. So here we can choose any element as our pivot, but here we choose the last element as our pivot. So 3 is the pivot, and as we discussed in our previous video that after we partition and reorder the array in such a way that all the elements smaller than 3 comes before 3 and all the elements greater than 3 comes after the 3. So it would look something like this, that this part is the left part and this is the right part and this is our pivot. So if you see, when this array will get sorted completely, so this is the sorted array. So here you will see that the pivot after the partition was at 4th index, and once the array got sorted completely, it was still at the same index, because when we partition the array in such a way that this condition holds true, which we discussed in our previous video as well, after the partition the pivot is actually at its sorted position. So now let's see how this partitioning happens. So here is the algorithm to partition the array. So friends, before we start, in case if you are new to my channel, then please subscribe to my channel and click the bell icon so that you never miss any update. Also please like this video and watch it till the end. So here you can see that let's suppose we are given with this array of 9 elements: 9, -3, 5, 2, 6, 8, -6, 1 and 3. So when we will call partition, we are actually partitioning complete array. It takes low and a high pointer. So low actually starts from the 0th index and high starts from the last index, because we need to partition the complete array. So low starts from 0 and high starts from 8. So when we do partition of the array, the first thing we need is the pivot. So we can select the pivot as the first element, last element, or any of the random element in this array. So here we will choose the last element as our pivot. So array value at higher index, which is the 8th index, will give us our pivot. So pivot is 3, this value, which is at array of high. Now after this pivot selection, what we do is we reorder this array in such a way that all the elements smaller than pivot comes in the left part, then comes the pivot, and all the elements greater than pivot comes at the right part. So this reordering is done by two variables I and j. Both are starting from low, which is the starting index of our array, or the starting range of the array from where we need to do the partitioning. So I starts from low, which is 0 index, and j starts from the low, which is 0 index. So friends, now we actually traverse each and every element of this array, and we provide a while loop where condition is I will traverse till it is less than equal to high. So friends, the basic idea behind this algorithm is why we are creating 2 pointers. If you see closely, then we have these 4 pointers. So usually from low to j-1, we actually have smaller elements and equal elements to pivot. Means all the smaller elements to pivot comes from low to j-1, including the elements which are equal to pivot. From j to I-1, we will have all the greater elements to pivot. And from I to high, the elements are yet to be traversed. So after every execution of while loop, you can see these conditions and you can figure out that how these ranges works. So at the start from I to high, every element is yet to be traversed, and low to j-1 and j to I-1 goes beyond the array. So therefore there are no elements in these ranges. Currently I is less than equal to high, so this condition is true. Now we are trying to explore the first element, which is 9. So here what we do is, in one of our previous videos where we saw that 3-number sort, or how we can sort 0 and 1, we apply the small part of the same logic here as well. So what we do is, this 9, which is at array of I, and this 3, which is our pivot, there can be two possibilities. Array of I can be less than equal to pivot, or array of I can be greater than pivot. So if array of I is greater than pivot, it means whatever value we have here, it is actually greater than pivot. So here you can see, we know that greater elements lies from the range j to I-1. So when array of I is greater than pivot, what we do is, we simply move I by one step, and if array of I is less than pivot, we perform a swap between I and j, and then we move j and I simultaneously. So you will understand why we are doing this once we perform few of these iterations. So at the start, array of I, which is 9, is greater than pivot, so this condition comes out to be false. So if array of I is greater than pivot, we simply traverse I ahead. I becomes 1, and we reach to index 1. So here you can see that why we actually traversed I one step ahead when pivot was lesser than array of I. 9 was greater than 3. So greater element should lie from j to I minus 1. So here you can see j to I minus 1. So this element. So this is the only range which can help us to figure out that it has the greater elements to pivot. You will understand more about these two ranges and these 2 points when we traverse ahead. Now I is less than equal to I, so this condition is true. Array of I is minus 3. Minus 3 is less than equal to pivot, so this condition comes out to be true. So when array of I is less than equal to pivot, we simply swap the value at I and jth index. So after we perform swap, we will see why we are actually doing that. So these 3 steps I will be going somewhat fast because we have already discussed how we can do this swapping. So minus 3 will come here and 9 will come here. Now after this swap, minus 3 has came here, 9 has came here. So here when array of I encounters a value lesser than pivot, it simply throws it into this direction, because from low to j minus 1 we need to put the smaller and the equal elements to the pivot. So how I can throw it in this direction is by swapping it with j, and after we perform this swap, we increment j and I both, because this value is placed at its proper position, that it is lesser than the pivot. So now we'll increment j also. So j becomes 1. And as these 2 elements are already explored, we will increment I as well. I becomes 2. Now our execution point reaches here, and here you can see that from low to j minus 1 we have smaller and equal elements to pivot. So from low to j minus 1, which is this element, this range are the smaller elements to pivot. From j to I minus 1, j to I minus 1, this element is in the range of the greater elements to pivot. So over these 2 conditions are still holds good. I is still less than or equal to I. So this condition comes out to be true and the while loop will execute. Now 5 is greater than pivot. So this condition comes out to be false. And once this condition comes out to be false, we know that we need to simply traverse I ahead. I becomes 3. So now here you can see this part is smaller elements range, and these 2 elements 9 and 5 are greater than pivot. So it is separated by j and I in such a way that from low to j minus 1 we have smaller elements. From j to I minus 1 we have larger elements. So therefore when array of I is greater than pivot, we simply traverse I ahead, we do nothing. And when array of I is less than equal to pivot, it means we have found one element lesser than pivot. So we simply throw it to the starting range and we simply shift the larger element range ahead. So here initially 9 was here, which was the larger or the greater elements to pivot. When we did the swap, 9 actually shifted in this direction, so that there could be a place for the elements which are smaller than pivot to come in this direction. So now similarly we will do this for the rest of the elements. From I to I, the elements are yet to be traversed. Currently I is less than equal to I, so this condition comes out to be true. 2 is less than equal to pivot, so this condition is true. So now here you can see, we know that 2 should lie somewhere in this range, at the starting range, and j keeps the track of the smaller elements from low to j minus 1. So at j we have one greater element and we need to put 2 somewhere here so that this 2 comes at its proper position, but here we already have 9. So therefore we do this swap so that 9 can come here and this range of the greater element is still maintained in the middle somewhere, and it simply shifts in this direction. So I'll remove everything. So now we'll do this swap. 2 will come here and 9 will come here. Two came here and 9 came here. So the range of greater elements simply shifted in this direction because we need to create a space so that smaller elements can come in this direction. We'll increment j now. We will increment I because this element which was here is actually being traversed. So from low to j-1 we have smaller elements range. From j to I-1 we have larger elements range or greater elements range. I is still less than equal to high. So this condition is true. 6 is greater than pivot. So this condition comes out to be false. It means 6 is at its proper range. We don't have to touch this. We will do I++. So I simply moves ahead. I becomes 5. Now this element also got into the range of greater elements because from j to I-1 we have the greater elements to pivot. I is still less than high. So this condition is true. So the while loop will execute. Now array of I, which is 8, is greater than pivot. So this condition is true. Therefore this condition comes out to be false. And as array of I is greater than pivot, we do nothing. We simply traverse I ahead. I becomes 6. And this element becomes part of our greater elements range. From j to I-1. I is still less than equal to high. This condition is true. Now -6 is less than 3. So therefore array of I is less than equal to pivot. Now we need to throw this pivot in the left direction. And we know that j is actually keeping the track of that. So this condition is true. First we perform swap between I and j so that this -6 comes in this range. And we simply shift the one of the greater element in this direction. So we'll perform this swap using a temp variable. So -6 came here and 5 came here. So after placing a smaller element at this spot, we will increment j. J becomes 3 because for the next smaller element, this would be the right place. So we increment j as well. And as we have already traversed whatever the value was here at this index, we will also increment I. So I becomes 7. So here you can see this range from low to j-1 we have smaller elements. From j to I-1 we have greater elements to pivot. Value of I is 7. So 7 is less than equal to high, which is 8. Now 1 is less than equal to 3. So this condition comes out to be true. We need to throw this 1 because it is lesser than or equal to pivot in this direction so that it can come in this range. We simply swap I and j. So 1 came here and 9 came here. So here you can see when we are actually encountering a value lesser than pivot, we are doing this swap and putting that at the starting range, and whatever value j is pointing from j to I minus 1, we have greater elements. So at j we have one greater elements. So we are simply shifting the range which is greater than the pivot just ahead. So 9 came here, but still if you see, the range is intact. All the elements which are greater than pivot are in sequence. The order will not be maintained, but the range will be maintained. So now after using this spot, we will increment j becomes 4, and we will increment I because this element is traversed and it got shifted here. So we simply traverse I ahead. I becomes 8. So here you can see from low to j minus 1, this range is of smaller elements. J to I minus 1, this range is of greater elements. Now for the last time, this while loop will execute because I is equal to high. So here you can see that now we are actually encountering the pivot itself, and this is one critical step because we need to put this pivot at its correct position somewhere between the range of smaller and greater elements to pivot's range. So this equal to condition does that, and it is very important. So currently array of I is equal to pivot. So 3 is equal to 3, which is the pivot. And we can place this 3 because smaller and equal elements to pivot will lie from low to j minus 1. And j is at the spot which can take lesser or equal values to the pivot. So 3 at index I will be swapped with j. So 3 comes here, which is our pivot, and 6 comes here, which is the value greater than to pivot. So after placing an element which is less than equal to pivot at its correct position using j, we will increment j so that next element can come here. But as there are no elements, but still we do this j++. So j becomes 5. And we will increment I because we are done with this element. So I becomes 9, which goes out of the boundaries of this array. So this condition comes out to be false because value of I is 8 and I is 9. So I is actually greater than I. So this while loop will terminate. And here you can see that in quicksort partitioning, when we do this partitioning, at the end we need to return the index of the partition, that from which index the partition is happened. So here we can see that from low to j minus 1 we have smaller and equal elements to pivot. So I will redraw this. Low to j minus 1, smaller and equal elements to pivot, j to I minus 1. So I value is 9. So j to I minus 1, which is still 8. These are the elements greater than pivot. And from I to I, we have traversed all the elements. So if you observe closely, j is actually pointing to a place where the next smaller elements to pivot will come. So we will simply return j minus 1 because we know that from low to j minus 1, we have elements smaller and equal to pivot. So 3 comes here, which is at index 4. So we will return the index of the pivot. So in this partition, whatever value we return is actually the index of the pivot after the partitioning, which is j minus 1. So index 4 will be returned. So this is how we do partitioning, and this partition method is very frequently used in the quicksort. Similar kind of logic is used when we do sorting of 0 and 1, or putting even or odd integers in certain sequence, or we sort the three elements 0, 1 and 2. So for 0 and 1, this code is pretty much similar. So this partitioning logic which you are seeing here is very important for many of the algorithms. And this traversal with this range is very important to understand because the same logic applies to many of the algorithms. So we will see the partitioning logic, how it applies to quicksort. In our next video, we will see that how this recursion happens, where we apply the same logic of partitioning in the left side of the array, which have smaller elements, and the right side of the pivot, which have the greater elements. So in this video, we are going to discuss about quicksort recursion. In part 2 video of quicksort, we discussed that how we can partition an array. So in this video, we will see that how we can perform quicksort recursion. So in the previous video, we discussed about the pivot selection, that we pick an element and mark it as pivot. The pivot can be any random element. It can be first element, last element, or any random element. Now based on what we choose as our pivot, we do the partitioning. We reorder the array such that all elements greater than pivot comes after the pivot. All elements smaller than pivot comes before the pivot. The elements equal to pivot can go on either side of the pivot. And once this partitioning is done, based on the reorder of the array, the pivot is actually at its correct sorted position. So this we already discussed in our previous video. So in this video we will be looking into the recursion part, where after partitioning the array, we perform these two steps, the pivot selection and partitioning, recursively on the sub-array formed on the left side of the pivot, which has the smaller elements to pivot, and on the sub-array formed on the right side of the pivot, which has the greater elements to pivot. So here about two steps we perform recursively on the left side of the pivot and on the right side of the pivot. So let's see at a high level how this recursion looks. So let's say we want to sort this array using quicksort. So here you can see that this is a small piece of code which does the sorting. It takes in an array and it takes in a range, that from which index to which index we need to do the sorting. And here you can see that the first step we are doing is the partition step. And once we get the partition index, now we have two arrays. One is on the left side of the partition and one is on the right side of the partition. So we recursively call the sort method, which is the same method, from low to p minus 1, which is the left part, and from p plus 1 to high, which is the right part. And this happens recursively because the method is calling itself again and again. After the partition, we are actually rearranging the array in the partition method in such a way that the element present at the partition index, which is the position of our pivot, that element is correctly sorted and placed at its proper position. So with one partition, we can get one element and place that element at its correct position such that that particular element is sorted. And we will keep on doing this recursion till low is less than high. So this is our base case. So at a high level, let's see how this recursion looks. In our next video, we will see the step-by-step demonstration of this quicksort algorithm. But for time being, we can just see at a high level that how this recursion looks like. So here at the start, we need to sort this complete array. So this will be our low and this will be our high. Now low is less than high. We call the partition method. So in the partition method, we take the last element as our pivot, like this. So 3 is our pivot. Now after this partition method will end, we get the index of the element 3 that where it belongs. So in our previous video we saw that how we can perform this partition, and we took the same example. So in the first partition you will see that 3 comes at index 4, and in the partition the array is rearranged in such a way that all the elements lesser than pivot comes in the left side, all the elements greater than pivot comes on the right side. So here we are doing the logical division of the array, and we are partitioning into two parts, left and right. So we are not breaking the array, it's just for the demonstration purpose that it looks like this. If you see the index from 0 to 3, we have smaller elements. From 5 to 8, we have elements greater than the pivot. So this is the pivot index. Now after we get the pivot index, if we sort this array directly, you will see that in the sorted array, 3 will be always at index 4. It means when we perform this partition, one of the element is sorted and it is placed at its correct position. So once it is placed at its correct position, we don't touch this element now. What we do is, we call the sort method on the left side recursively. So it goes deep down like this, and the range we took is low to p minus 1. So p is the pivot and this is p minus 1. So now we will call the sort by taking this left side, only these 4 elements, and this will happen recursively. Low should be less than high, this would be our base case. So here when this sort method will be executed for this left array, you can see that this sort method will be executed again. Low will be the same, but high will become p minus 1. So this would be our high. Low is less than high. Now we will again call partition method. We will pass in the array. We will pass in low and high. So now in the partition method, only these 4 elements will be reordered because we are providing the range of low and high in the partition. At the start, low and high were the complete range of the array from 0 to 8. Now this partition method will only partition 0 to 3. So in the partition method, we will first choose the pivot element, which we have discussed that we choose the last element. Now we need to do the reordering such that all the elements lesser than 1 should come on the one side and all elements greater than 1 should come on the other side. So here you will see that the partition method will reorder the array in such a way that it looks like this. This much part are the elements which are lesser than pivot, and this much part are the elements which are greater than pivot, which is 1. But here you will see the index which we get is 2 because it returns the final position of the pivot. So index 2 will return. Here in the first partition index 4 was written. So based on this p minus 1, we took the left side of the array and we did the partition again. So now here if you see, if we sort this array completely, you will find that 3 is at 4th index, which is sorted, and after the second partition 1 will be at 2nd index. So this element is also sorted. So now we don't touch 1. Here if you see, we again go on the left side from low. So this was our low and this is our p and this is our high. So we again call sort method from low to p minus 1, which is we are taking the left side of the array. So when this sort method will be called again, low will be at the same spot but high will become this spot. So it means now we are actually picking up this 2 elements and we are trying to sort them and we are trying to apply this logic. So this will be our low and this will be our high. Low is less than high. So it means we have 2 elements. So we can again do the partitioning of the array from low to high. So in the partition method, we will take the last element as our pivot. And now we will partition the array in such a way that all the elements lesser than minus 6 will go on the left side and all the elements greater than minus 6 will go on the right side. So this partition method will reorder only these two elements now, because we are providing the ranges, and it will touch the array into these ranges only. So it looks like this. So as there are no elements which are smaller than -6, so -6 will be the only element on the left side which is at index 0, and -3 is greater than -6, so this will lie on the right side. So friends, here you can see that now this is our low and this is our pivot index. So after we get the pivot index, we will again call sort on this one element. We will try to sort its left part from p-1. So p is at 0 index. If we do p-1, it will go -1. So here if you see, when we partition the array, pivot was at 0th index. It is the only element now. So on the left side of pivot, we have no elements. So if we call sort method again, passing in low as 0 and high as p-1, so it will take the value of the new high as -1. So here we will reach the base case and we will simply return from this method, because low value is 0 and high value is -1. So therefore we can't further divide -6, and at whichever index -6 will be there, that will be the properly sorted position for the element -6. So now this method is done, because when we call sort again, we will reach this base case and we will return. So this method will be done. So now this sort method will be executed and we go to the right side of the pivot. It means now we are taking in the elements which are greater than -6, which is the only element -3. So p plus 1 will be our new low. This will be our low, and high will remain the same index. So here if you see, we will again encounter the base case. Low is actually equal to high. So it means we can't divide from low to high further down. So based on this base case, this sort method will end and the call will reach here again. And the sort method which we called from here, this will also get end. So -3 will be also at its correct sorted position, like this. So here with these two sort methods, we are going in this direction and then we are going in this direction. So with this sort, we went to this direction, this is sorted, and with this sort, we went to this direction, which is sorted. So we will return back to the left side, and here you can see when we will return back here, when we had called sort on this part, we went in this direction, and as we are returning back from here, so we will return from here like this. And now when these two elements are sorted, we will go in this direction to sort the greater elements to this pivot, because we are doing this algorithm recursively. So first the left side is done, and once that left side is done, we go on the right side. So this side is done completely here. Now we go on this side. So here 2 is the only element left. So this will be sorted because the base case will be fulfilled. For this element, low and high will be at the same spot, because this is our P, and if we are going on the right side, we do P plus 1. So P plus 1 will be the index 3, which will be our low, and high is already at index 3. So this is sorted like this. So now execution point will reach back here, and here you can see left side is now properly done. So it will go back here, and now we perform the same steps recursively on the right side of the elements which are greater than 3, which is at index 4. So now we perform the same step on this right side. So if we are going on the right side, we are doing P plus 1. We are going on the right side. The low will be from P plus 1 to high. So this is P. This will be our low. And this will be our high, because this high has not changed its value. So now we will partition it again based on what we saw here. So 6 will be the pivot, and now when we will partition it, it would look something like this. So 6 is properly sorted, Now we go on the left side first. So 5 is the only element left. So it will encounter the base case. This is our P and this is our low. So for the left side, if we do P minus 1 to take all the elements which are lesser than 6, this will become our high. And as high is equal to low, we will return from the recursion and phi will be at its correct position. So we go back like this and then we try to sort the right side. So we call the recursion again by taking P plus 1 to high. So this was high. Like this, and if we do P plus 1, this will be our low now. So now we are actually partitioning two elements. So we take 9 as the pivot. We do the partition. So our pivot lies at the 8th index. There is only one element which is lesser than pivot, which is on the left side of the array. And there are no elements which are greater than pivot. So after the partition, at whichever position the pivot lies, this is the properly sorted position for element 9. And we are left with only one element. So we first go on the left side like this. We take from low to P minus 1, because if we do P minus 1, we'll get the left side range. So this will become our new high. And as this is the only element left, low is equal to high. So we can't divide or partition this piece of sub-array further. So 8 will be also at its correct position like this. So if I remove everything, so here you can see that we are performing the recursion on this array recursively and we are doing the partitioning, and with each partition one element is getting sorted and placed at its correct position. So if you try to combine all these indexes, you will see that if we sort this array, the array would look like, if I just plot it here, it will look like first minus 6, minus 3, then 1, 2, 3, 5, 6, 8 and 9. So if you see that this would be our finally sorted array, and if you see the indexes of all the elements from 0 to 8, you will see that at 0 we have minus 6 like this. At index 1 we have minus 3 sorted. Index 2 we have 1. At index 3 we have 2. Index 4 we have 3. At 5th index we have 5. 6th index 6. 7th index we have 8. And at the 8th index we have 9. So here you can see that how this recursion and this partitioning is helping us to perform the quicksort. So friends, here if you see, at the start we took complete array, we took a pivot, we did the partitioning, all the elements lesser than pivot were on this side and all the elements greater than pivot were on this side. Then we recursively took the left part, we took the pivot and we did the same steps like this. Then we took the left part again, we did the same steps, and finally we got minus 6 and minus 3 at 0 and 1 index, which are sorted. And after taking this left and right part and sorting them, this left part was done properly. Then we picked the right part of this pivot and this was sorted. And after we sorted this, all the elements were done for the first left sub-array. Then we went to the right part and we did the same steps again. We first went on left, then we went on the right. We first went on the left, then we went on the right. And at the end, you see all the elements are at their proper indexes. So if we sort this array, you will get this array. So friend, this was all about the quicksort recursion. If you didn't understand any of the recursion logic here, in our next video, we are going to see the step-by-step demonstration of the quicksort algorithm. there it will make sense that how this recursion is happening, where this sort method is again calling this sort method 2 times. After partitioning, we go on the left side first, and then we go on the right side. So we will understand this recursion in our next video with a detailed demonstration. So now in this video, we will see the step-by-step demonstration of the quicksort algorithm, and we will see that how the algorithm works via an animation. So this is the quicksort algorithm, and we will see the step-by-step demonstration of the algorithm. So friends, before we start, in case if you are new to my channel, then please subscribe to my channel and click the bell icon so that you never miss any update. So in quicksort algorithm, we have this sort method which takes in an array which we want to sort, and we pass basically a range that from low to high we need to sort. So at the start, let's say we want to sort this array having 6 elements 5, 2, 0, 1, 6, 3. So when we will call sort method, we will pass in the array. The low will be 0 and high will be array.length -1, which is the last index. So low is 0, which is pointing to 0 index. High is 5, which is pointing to the last index. So we are telling that we need to sort this array completely from 0 index to 5th index. And here you can see that this sort method is recursively calling this sort method again here and here. So in order to demonstrate the recursion, we are using this call stack, which will have the method calls and the state of the method stored in low, p and high. So when this sort method will be called, there will be one method on the call stack by name sort. Low is at 0 index, high is at 5th index, and p is the index of the pivot which we will be calculating here. Moving ahead. So here we know that quicksort is divide and conquer algorithm. So here we actually divide this complex problem of sorting into smaller sub problems, which means that we are dividing this array into 2 parts, and we keep on dividing the array into this recursive sort methods based on range low and high. So when low will be equal to high or low will be greater than high, when low will be equal to high, so it will be something like this, that low is equal to high. It means we can't further break down the array because it has only one element. So therefore, when this condition will arrive, we need to simply break from this recursion, because this sort method is recursively calling this sort and it keeps on going. So when low will be equal to high or greater than high, then we need to tell recursion that we have reached our base case and we need to stop the recursion. So currently low is less than high, low is 0 and high is 5. So this condition comes out to be true. So friends, in our previous video we discussed that how we actually do the quicksort. We first do the pivot selection, where we pick up a random element from an array and then we actually partition the array. And we partition the array in such a way that the elements which are smaller than the pivot usually lie on the left side, and the elements which are greater than pivot usually lie on the right side, and the equal elements can go on either side. So here this is the first step. We actually call the partition method. We pass the array. We pass the range from low to high. So currently we are telling that we need to partition this complete array. And in this partition method, we actually do the pivot selection and reordering of the array. So this method we have discussed in our previous videos in a greater detail. You can watch that video to get more understanding. But here also we will see that how this partition works. So when we will call partition method, we are leaving this sort method. So the execution point will leave the sort method and the partition method will be on the call stack. So before we leave this sort method, we need to store the state of this sort method, that low was at 0 and high was at 5th index. And as we are leaving this sort method, we need to keep the track of line number, because once this partition method will end, we need to begin this sort method from line number 3 only, because we are leaving this sort method at line number 3. So here we will update the line number 3 like this, which tells that we are leaving this sort method at line number 3, and when we will come back to this sort method, we will start our execution from line number 3, and when we will start our execution, low will be at 0 and high will be at 5. So we are simply storing the state here. So now we'll see this partition method with this array, low as 0 and high as 5. So we are partitioning this complete array. We have discussed this method in greater detail in our previous videos. You can watch that video so that once we go through it again, you will get more better understanding. So first we do the pivot selection. We can choose any random element from the array as our pivot. We can choose the first element or any element in the middle or the last element. So here we choose the last element as our pivot, which is denoted by the end of this range. So pivot becomes array of high, which is 3. So this is our pivot. And after this pivot selection, our job is to do this partition. Elements lesser than 3 will go on one side, which is on the left side. Elements greater than 3 will go on the right side. And the elements which are equal to pivot can go on either side. So when we perform the partition, we take the help of two variables I and j. Here I and j both starts from low. Currently low is pointing to 0 index. So we are not starting I and j from 0th index. We always start it from the low index. Because currently as we are partitioning complete array, low is pointing to 0. There could be a chance that we only need to partition these 3 elements. So at that moment, low will be at 3rd index. So we need to partition from 3rd index to 5th index. So therefore we create 2 pointers I and j, both starting from low. I is 0 because low is pointing to 0. J is 0. Now as we need to partition, we need to provide a while loop where we traverse each and every element of the array. Using the iterator I, it goes till it is less than equal to high. So this is very important algorithm and it is used in many problems. Here what we do is, we have these 4 pointers and once we partition the array, it looks something like this. Smaller and equal elements to pivot are on the left side. Then we have the pivot and then we have the elements greater than pivot. So this is the ranges, and if we use these 4 pointers, the range varies like this. From low to j-1 we have smaller elements or equal elements to pivot. From j to I-1 we have the elements greater than pivot, and we have discussed this in greater detail in our previous videos as well. From I to high we have elements yet to be traversed. So at the start we need to traverse every element. So from low to j-1 and from j to I-1 we don't have any elements because all the elements are yet to be traversed. Therefore we have provided this condition that this while loop will run till I is less than equal to high. So we'll see how this algorithm works. And also we need to keep this if condition in mind. So here when we are partitioning, we need to compare each and every element with the pivot. And if it is less than pivot, the first thing we do is we simply swap the values at I and jth index in the array. Because as this element is less than equal to pivot, it should come at the starting range because we need to partition it that way. So we will see how these 3 steps work. And if the element is greater than pivot, we do nothing. We simply leave the element there and we traverse I ahead. So this condition is true, I is less than equal to high. So in the if condition we check whether array of I is less than equal to pivot or not. So we are simply checking whether 5 is less than 3 or not. So 5 is greater than 3. So this condition comes out to be false. So when array of I is greater than pivot, which is our case, we simply leave that element there and simply traverse I ahead. So I becomes 1. I is still less than equal to I. Now array of I, which is 2. 2 is less than 3. So this condition comes out to be true. And once this condition comes out to be true, we know that we need to swap the values at I and j index. It means we need to swap 5 and 2. So here, why we are doing this swap is, we need to partition the array in such a way that smaller element should come at the starting range. Then our pivot should come, and then the elements greater than pivot should come. So when array of I is less than equal to pivot, we simply throw the element which is at ith index to jth index and take its value. So when we will do this swap, I will go over these steps quickly. 5 will come here and 2 will go there. So 2 came here and 5 came here. And we know that now we need to increment j and I both. So why we are incrementing j is because j has placed one of the smaller elements here. So this space is occupied. So j moves ahead. J becomes 1. And we will simply traverse I also ahead because this element is also explored. So I becomes 2. So friends, one thing to note here is, irrespective of any of this condition is met, we simply traverse I ahead in both the cases. So therefore it is written here. Now I is less than equal to I. Array of I, which is 0, it is less than 3. So this condition comes out to be true. So we need to throw 0 to j and take its value by doing this swap. So 0 goes here and 5 comes here. So friends, here you can see that as 5 is greater than pivot, the elements which are greater than pivot, they are actually shifting in this direction. But the element which are lesser than pivot, we are simply throwing it to j to put it at that particular index, and j actually holds one of the greater element to pivot. Because from j to I minus 1, we have the elements greater than pivot. So j is actually pointing to one of the greater elements than pivot. And once this swap is done, we are simply taking a greater element and shifting it ahead. And by doing this swap, we are creating one space here so that the elements which are lesser than pivot can come here. So therefore we do the swap. We throw whatever the element is at the ith index to j and take its value. So this spot is filled now properly. So we will increment j. So j becomes 2. We will increment I. I becomes 3. This condition is still true. I is less than equal to I. 1 is less than 3. So this condition is true. So we perform these steps again. So we are performing this swap using this temp variable. So 5 comes here and 1 goes there. And after filling this position with a value smaller than pivot, we move j ahead. So j becomes 3. And we have explored the array till this point, so we move I also ahead. I becomes 4. So friends, here you need to keep watch on these two ranges. From low to j minus 1, we have the elements smaller than pivot, which is true. From j to I minus 1, we have elements greater than pivot. So this is j, I minus 1. So 5 is actually greater than pivot. So this both the conditions are true when we are doing these steps. Now I is still less than equal to I. So this while loop will execute. Array of I, which is 6, is actually greater than pivot. So this condition comes out to be false. So when array of I is greater than pivot, we know that this element is greater than pivot and it is at its proper position. So we don't touch this element. We simply move I ahead like this. So still you can see from j to I minus 1, we have elements greater than pivot. So therefore when we encounter a value greater than pivot, we simply move ahead. And when we encounter a value lesser than or equal to pivot, we simply throw it into this direction so that we can perform a swap between I and j. Now I is actually equal to high, so this loop will run one more time. And now here you can see our pivot and array of I are the same elements. So why we are running it one more time is because smaller than or equal to pivot. So we have got a value equal to pivot. So we need to make it lie in the range of low to j minus 1. So j is holding a value greater than pivot. So we do this swap here. So 5 comes here and 3 goes there. So it means our pivot has landed into its correct position. Then we will increment j. J becomes 4. And we will increment I. I becomes 6. So as I has become 6, this while loop will terminate because value of I is 5. So friends, this partition method does two things. First, it returns the index of the pivot, which is j minus 1, which is 3. And second, it takes in the original array and reorders it such a way that all the elements smaller than pivot are on the left side and all the elements greater than pivot are on the other side. So when this method will end, we will return j minus 1, which is the index of this pivot from where this partition has happened. So the execution point will reach to this sort method and the array has been reordered. We have left this sort method at line number 3. So we will start from line number 3. This partition method has written a value of p, which is the index of pivot, which was 3. So value of p will be 3. Like this here. So this is what we saw in the partition, that all elements smaller than pivot are in this side and greater than pivot are on this side. So friends, here you can see that if I sort this array directly, the sorted array would look like 0, 1, 2, 3, 5 and 6. And here you can see that once this partition is done, when we are putting all the smaller elements before the pivot and all the greater elements after the pivot, so when we sort this array completely, you can see that the index of the pivot remains the same. 3 is at index 3 and after sort also it will be at the index 3 because here it's 0, 1, 2, 3, 4, 5 index. So it remains at the third index only. So this is one important step in the partitioning, that after the partition, pivot is actually at its sorted position. So now what we do is we don't touch this pivot because it lies at its proper sorted position. Now our task is to perform this pivot selection and partitioning on the left side of the pivot and on the right side of the pivot, and that too recursively. So this sort method will keep on calling itself till the base case is reached. So now we call the sort method again, and this time we only take these 3 elements and we try to sort them. So here we are calling this sort method, we are passing in this array. Low value will be 0 only, high value will become p minus 1 because we are calling this sort method with p minus 1. It means we are taking in this range. This is p, so this will be p minus 1. So when this sort method will again gets called, our high will become p minus 1. So as we are leaving this sort method and we are calling this sort method, so first we will update the line number here, and we are storing the state of the low, p and high. So we update line number 4 here, and we leave this sort method and again call the sort method. So this sort method will be called with low as 0 and high as p minus 1. So this was our p previously, p minus 1, which is 2. So here now we are doing the sort from low to p minus 1. So this is the range of our array which we need to sort now. So high becomes 2, p minus 1 which is 2. So our new high became 2. Low is less than high. So now we'll partition only the left side of the pivot, which is these 3 elements. So we will leave at line number 3 this sort method. So this partition method will be executed again, and now we are not taking in complete array. We are taking the array from range low to high, which is 0 to 2 index, like this. So this partition method will only touch these 3 elements. So first we select the pivot, which is the last element of this range. So array of high will become our pivot. So 1 becomes our pivot. We start the partitioning with a value of I and j as low, which is 0. And as we already discussed how this algorithm works, we'll go over this quickly. We need to keep these ranges into mind and these two conditions into mind. So I is less than equal to high. This while loop will execute. Array of I, which is 2, it is greater than pivot, so we do nothing. We simply move ahead. We do I plus plus. I becomes 1. I is still less than high. Now array of I, which is 0, it is less than equal to pivot. It means we need to throw it to j and take its value. So we do this via a swap. So 2 comes here and 0 goes there. So 0 goes there. And as j has filled this position properly, we'll increment j. J becomes 1. We'll also increment I. I becomes 2. I is actually equal to high. So this loop will run one more time to put this pivot at its correct position. Now 1 is equal to pivot. So we do this swap again. So 2 comes here and 1 goes there. Then we increment j. J becomes 2. And we increment I. So I becomes 3. And this while loop will terminate because value of I is 2 and j is 3. So 3 is not less than equal to 2. So here you can see that now we need to return the index of the pivot, which is at j minus 1, which is this. And here you can see that when we did partition of these 3 elements, these are actually elements which are lesser than pivot, which is 1, and these are the elements which are greater than pivot, which is 2. So currently it has only one element. So we have reordered the array and we are returning the pivot as 1. So execution point will reach here. We know that we have left at line number 3. So we start from here. this method returned the value of pivot as 1. So P becomes 1. Like this. So friends, we know that after doing this partition, we recursively call the sort method again. And this time we go from low to P minus 1, which is the left side. And then we go from P plus 1 to high, which is on the right side. So first we go on the left side. So here you can see this recursion is happening till the array is getting divided. So now when we will leave this sort method, we will first update the line number here, which is 4. And then we will call this sort method where low will be 0 and the value of high we pass as P minus 1. So P minus 1 will be 0. So this value will go to high and this value will go to low in the next sort method. So we have updated the line number and we have called this sort method again. So it looks like this, that this low which was 0, it's 0, P minus 1 which is 0 index, so high becomes 0. So it looks like this. So friends, here you can see now low and high are pointing to the same index. It means that we have left with only one element and we can't divide this array further down or partition this array further down because we have only left with one element. So therefore we have reached our base case. So low is equal to high. So this sort method will end and this sort method will be removed from the call stack and the execution point will reach here back. So it looks like this. This method was removed from the call stack and execution point reached here. We know that we left this sort method at line number 4. So we start from line number 4. And when we had left this sort method, low was at 0, P was at 1, high was at 2. So we position them back to their respective indexes. High was at 2, P was at 1. And here you can see that we are done with this left part now. So this sort method is done. And now we go on the right side. So we call this sort method again. Now this time we are passing the value of low as P plus 1. So P is 1 and P plus 1 is 2. So when we go on the right side, the value of low changes, and when we go on the left side, the value of high changes. Here you can see, if you are going on the left, value of high changes. If you are going on the right, value of low changes. So now we will leave this sort method. We first update the line number here, that we are leaving at line number 5. And we are calling this sort method with P plus 1 as our low, which is 2, and high as 2. So there will be one more method on the call stack with low as 2 and high as 2. So it would look something like this. Moving ahead, here you can see that now we are actually partitioning the elements which are greater than pivot, which is only this element 2, which is only one element. As low is equal to high, it means we have reached our base case and we are telling to this sort method that please stop the recursion and go back. So this method will be removed from the call stack because we can't divide 2 further down. And the execution point will reach here. So when this sort method was left, we had left at line number 5. So we start from line number 5. And at that moment, value of low, P and high were 0, 1 and 2. So we give them their respective indexes. So it was like this. And now after executing line number 5, there are no more lines left to be traversed. So this sort method will also end and the execution point will reach to this sort method because this sort method was actually being called by this sort method. So this method will be removed from the call stack. And when we had left this sort method, we had left at line number 4. So we start from line number 4. And at that moment value of low was 0, P was 3 and high was 5. So we give them their respective indexes. So this was the state when we had left this sort method. So here this sort method is done. It means that when we had done our first partition, the pivot came out to be index 3. And in this sort method, we went to the left side of the pivot and we did the sorting. And here you can see these 3 elements are sorted. So we had done with this method. Now our task is to go on the right side, call sort method again recursively. We pass the value of low as P plus 1 because we need to now go in this direction, and high remains the same. So here we are leaving this sort method. We'll update line number here, which is 5, and we are calling this sort method, passing in low value as P plus 1, which is 4. So it looks like this. Low becomes P plus 1, which is 4. So it looks like this. Low is less than high. It means we have 2 elements. It means we can divide this 2 elements further down. So we call the partition method again. We pass in the range from low to high. We are telling we need to partition the array of these 2 elements only. So this is our range. So when we are calling this partition method, we first update the line number here, and we have stored the state already in low and high. So line number 3 comes here. We leave this sort method. We call this partition. We need to partition from low to high. That is in this range. We are not touching this side because we have already done the sorting and partitioning of these elements. So we are now only touching these 2 elements. Array of high will be our pivot. So first we are doing the pivot selection. So 5 becomes our pivot. We create 2 pointers I and j, which start from 4th index. And then we perform the same step which we have discussed already. We provide a while loop and the condition is I should be less than equal to high. We need to keep 4 things in mind. These 2 ranges and these 2 conditions. So array of I, which is 6, it is greater than pivot. So we simply traverse ahead. We do nothing. We do I plus plus. I becomes 5. I is equal to high. So this condition is true. Now array of I is 5 and 5 is our pivot as well. So therefore, when array of I is equal to pivot, we need to throw whatever value is at ith index to j and take its value. So we first perform the swap. So 6 comes here and 5 goes there. We have placed 5 at its correct position, which is our pivot position. So we increment j. And then we increment I. So now this while loop condition comes out to be false because value of I is 6 and high is 5. So we simply return the pivot index which is at j minus 1. So j minus 1, which is the 4th index. So we return 4 from this partition method, and we have also reordered the array in such a way that all the elements lesser than pivot are on its left side. So currently there are no elements which are lesser than pivot because we are not touching this side, we are touching from low and high. So from low to j minus 1, we have elements smaller than or equal to pivot, which is true. And from j to I, which is 6, minus 1, which is only this element, having a value greater than pivot. So we simply return index 4 from here. So the execution point will reach here. We had left this sort method at line number 3. So we start it from line number 3. The partition method returned the value as 4. We have placed 4 here. So P becomes 4. Now we go on the left side of the pivot from low to P minus 1. So here you can see low and P are pointing to the same element. So when we call this sort method, we first update the line number, which is 4. And then there will be one sort method on the call stack. So here, when we had left this sort method, we called this sort method from low to P minus 1. So when we did P minus 1, our high became 3. So here you can see that low is actually greater than 3. So it means we have reached our base case, and which makes sense because there are no elements on the left side of the pivot to be divided further down. So we simply return from this method, and the execution point will reach here. We had left at line number 4. So we start from line number 4. And low P and 5 had values as 4, 4, 5. So we give them their respective values. 4, 4 and 5. And now we go on the right side of the pivot, which is at P plus 1 to high. So P plus 1 is index 5. So first we update the line number here, because we are leaving this sort method. And then we are calling sort. So there will be one more method on the call stack with P plus 1 as our new low, which is 5, and high remains 5 only. So it looks like this. So here we can't divide this 6 further down. It means we have reached our base case. Low is actually equal to high. So this if block will not be executed. So the condition in if block comes out to be false, and we simply leave this method. So this method will be removed from the call stack, and the execution point will reach here. We had left this sort method at line number 5. So we start from line number 5. And at that moment, low, P and high were at 4, 4 and 5th index. So we reassign them their indexes like this. And as there are no more steps left to traverse for this sort method, so this sort method will also be removed from the call stack, and the execution point will reach here. So when we had left this sort method, we had left at line number 5. So we start from line number 5, and at that moment low, P and high were at 0, 3 and 5th index like this. And also friends, here you can see that after line number 5 we have no statements to execute. So this sort method will also be removed from the call stack. So friends, here you can see after every method got removed from the call stack, we have actually performed the sorting of the array. We have used the quick sort and we have sorted the array. So friend, this was all about the step-by-step demonstration of quicksort algorithm, where this sort method recursively calls this sort method. One is when it goes on the left side of the pivot, which is the smaller elements, and one when it goes on the right side of the pivot, which are the greater elements to pivot. In this partition method, we do the pivot selection and reordering of the array in such a way that smaller or equal elements are on the left side. Then our pivot comes, and then the elements greater than pivot comes. So this steps we do recursively till all the elements are sorted. So friend, this was all about quicksort algorithm. I hope you must have liked this video. In case if you are new to my channel, then please subscribe to my channel and click the bell icon so that you never miss any update. Thanks, have a nice day.